Understanding and explaining Bernoulli's equation is one of the important outcomes for this course. So this time we're going to take a look at deriving Bernoulli's equation via vector calculus. And to do that, we'll start with the Navier Stokes equation written in vector form. This equation tells us that the acceleration of a particle depends on the applied pressure forces, gravitational forces, and viscous forces. If we have no energy lost or gained, then these viscous forces will be canceling out because those are our losses. If we divide by density, to simplify, and expand this term in here by a vector identity, which you can find in just about any mathematics textbook, then we'll wind up with du dt plus, and this is where the expansion comes in, grad a half u dot u, both of those are vectors, minus u cross grad cross u. Now this may not make a lot of physical sense to look at, but it's mathematically correct by this vector identity that we've used for the expansion. And that's going to allow us to simplify quite a bit later on. And that will still be equal to the gradient of the pressure divided by density, and if we're in an incompressible flow, density can move in and out under these gradient operators, plus the gravity vector. Now remember, gravity will be equal to negative g, just 9.81 meters per second squared, times the gradient of h. This is the elevation, so the gradient is the change in the elevation. Collecting again, du dt plus grad p over rho plus this term here, that grad 1/2 u dot u, and with g coming in here, that'll be negative g grad h, so this will be, when we take it to the other side, positive g grad h, all equal to u cross grad cross u. This thing that we got out of the identity here that we're not quite sure what to do with, but we'll carry it along for now. Now if this is a steady flow, then the time derivative will drop out and we'll be left only with these terms. We've got the gradient operator here in all of these, so we could take that all together as the gradient p over rho plus a half u dot u plus gh. And that'll all still be equal to that u cross grad cross u. This vector quantity we're not sure what to do with it. But if this equation is true, then we can take a dot product of this equation with the velocity vector. So if we'll just u dot, and over here also u dot, taking the dot product of both sides. That's going to give us the advantage that this dot product here of u with this other vector quantity will be 0 if this other vector quantity is perpendicular to u. And the cross product of u and any vector is perpendicular to u. So the dot product of this vector quantity, which is perpendicular to the velocity vector, is equal to 0 because of that characteristic. So now we've got u dot grad p over rho plus a half u dot u plus gh equal to 0. This is starting to look like Bernoulli's equation. We've got a pressure term, we've got a velocity squared term, and we've got an elevation term. Now u dot grad is a steady Lagrangian derivative for a particle. So this is taking the steady Lagrangian derivative of whatever's inside the brackets here. And that's saying then that if we follow that particle, then that total quantity will be a constant. Now we're in a steady flow, and in steady flow, a particle follows a streamline. Path followed by a particle goes along a streamline. And the dot product of the velocity with itself anywhere is the square of the magnitude of the velocity. So u dot u we'll call capital V squared, and because we're in steady flow, particles follow streamlines. Thus, along any streamline between 2 points, this quantity will be a constant. That means that h1 plus p1 over rho g plus v1 squared over 2g will be equal to h2 plus p2 over rho g plus v2 squared over 2g. And that's our Bernoulli equation. So we got to Bernoulli's equation fairly directly by a vector calculus. And it still means the same thing: potential energy of elevation plus potential energy of pressure plus kinetic energy associated with the motion of the flow has to remain a constant. They can be converted one into the other, but for any one particle, this energy will be conserved unless we have a mechanism like this one to add or remove energy from that particle. Now, I find this calculus quite convincing, but I find it even easier to understand when I explain it physically with particles gaining and losing energy. You don't need to be able to do this vector calculus for Mech 241, but if you already feel better about large equations like this and deriving your equations directly from them by vector calculus, then I hope this will help you to better understand Bernoulli's equation.